Thank you very much, Arun. Appreciate that, and thank you everyone for joining today. So what I was asked to cover was to give you a sense of what some of the emerging trends are in IT and data in the enterprise, so that you could become aware of that as well, and direct some of your efforts to position yourselves for what might be emerging as a whole new set of demands and needs for particular skills. So the one I'm going to focus on is in the area of data science and machine intelligence. So I think that it's important to look to where essentially the puck is going to be in order to give yourself some time to position yourselves to be able to fulfill that particular need. And that's what I'm going to give you a sense of during this presentation. So what we're going to do is we're going to cover what machine intelligence is, what are semantic knowledge graphs, what is machine learning, what is natural language processing and cognitive computing, what are some of the use cases that use these technologies, and how do you really prepare yourself? What skills are needed, and what can you do to pick up skills in order to fulfill some of these new and emerging needs? So I'm going to try to fill this with a lot of information in a short amount of time, but it's just to give you a sense of the scope of the space, not as much for you to actually digest in particular and learn anything in detail. We're just going to cover a lot of territory at 100,000 feet. So first of all, let's start with the definition of machine intelligence. What is it? So it's first, I would say, the ability for machines to represent knowledge and to reason. And we can look to semantic technology for that particular aspect. And then the ability to capture and understand human intent, context, and communications is all around natural language processing, text, and multimedia analytics. And then to learn, to predict, and to recommend is all about machine learning. And then cognitive computing, which we'll cover in a bit, is all of the above while incrementally improving over time with new experience. So we'll cover that. Let's start with semantic knowledge graphs. What are they? But to put that into a context, you have to first look at big data. So we would say that big data is the big enabler of all of this. Without big data, all of these technologies would be needed, but having big data puts the need somewhat on steroids, because as a result of big data, we're able to consume vast quantities of information at a very rapid pace. And the thing here is that we're absorbing large amounts of unstructured content from text and voice and video, along with all kinds of semi-structured and, of course, structured data. We're just absorbing huge amounts of information, which presents a huge challenge. So some of the big limitations with big data is that executives expect this beautiful data lake that will provide insights and information on demand that they never had before, and that's of course a reasonable expectation. But in reality, due to many issues with disparate data, we instead get or start out with a data swamp, because we're dumping all kinds of content into our big data environment. We're not getting the clarity that we often need. So big data by itself is very raw, it's highly disparate, highly variable, and it's very difficult to integrate and harmonize it so that we could take all the pieces and put it together in a very clear, meaningful picture. So in order to make sense of all the content we put into big data, you think of the analogy of garbage in, garbage out. Big data is a very, very inexpensive garbage bin, essentially. And how do we turn that into gold, essentially? How do we mine the gold out of that? So it requires a schema to make sense of all of that content and metadata. But with big data, because we're absorbing so much data quickly, the schema is applied after the data is basically ingested rather than before, as is what is common with conventional systems like relational database. So I want to introduce you to semantic knowledge graphs, because what they do is they allow us to understand the content that is in big data, and they allow us to define a schema after the data is stored in big data so that we could better understand what it is. So semantic knowledge graphs are really not new. They're already in use. IBM's Watson initiative, where the two expert humans in jeopardy, makes use of knowledge graphs. Siri, which actually came out of SRI, one of the founders of the technology behind Knowledge Graph was the chief technology officer of Siri before it was sold to Apple. Google recently coined the term knowledge graph. So Google makes extensive use of this technology, as does Facebook. So what is a knowledge graph? And in particular, I'm going to talk about semantic knowledge graph. So basically, what it is it's a very intelligent model or schema that allows us to specify and define concepts based on common meaning. So it gives us the ability to define basic concepts like what is the meaning of a customer, what is a automobile. All kinds of things can be described in an ontology, and the cool thing about these is that it's not only visible for humans to understand, but it allows machines to understand it as well. So it allows us to create in this knowledge base or knowledge graph a single version of the truth. In finance, what is a credit default swap? You only have to define it once in the knowledge base or ontology or knowledge graph. They're all synonymous. And you don't have to write the logic in an application program. So as a result, you can get really high reusability that's been verified. So we'll see inevitably a reduction in software costs when we start to use these ontologies more and more. And we'll also have much faster time to market because we don't have the brittleness of current conventional database technology constraints, such as in relational database, where you have to define your ideas into a model, into a schema, and define the physical organization of that in a table. That takes days, weeks, sometimes months before you can even load data. With semantics, you can load the data before you even need to figure out how all the parts are interconnected, and you don't have the constraints of a database. You can do this almost virtually. There's also inference that we'll talk about. So what is what we'll call an ontology or a semantic knowledge graph? So ontologies are, again, very expressive schemas that represent the meaning of things. So let's look at a concept of employment as an example. So with ontologies, semantics, everything is linguistically aligned with how we think and speak, like sentences, like grammar, subject, predicate, object, basic grammatical structures, where we could say in a sentence, a person works for a company. That could break down into subject, predicate, object. And that's the basic underlying form of an ontology. It's called a triple. And then you could weave in additional concepts. For example, is employed by, we could call a subproperty of works for. It's a kind of works for. So we could say that if a person is employed by a company, we could infer that person must work for the company. Already this is a set of concepts that that is very difficult to do with conventional technology. You could then weave in other concepts, such as employees is the polar opposite and inverse of employed by. So if we could say a person A is employed by company B, we could then infer that company B employs person A. Then we could assert facts. We could do this either before or after. So we could say here that this person is a type, this is a type of person. Wells Fargo is a type of company. Actually, that's me. David is a type of person. And we could assert that David, a type of person, is employed by Wells Fargo, a type of company. Therefore, David works for Wells Fargo. Therefore, Wells Fargo employs David, and David also will play the role of an employee, and Wells Fargo therefore must play the role of an employer. So we could define all of these relationships for one thing. It becomes very expressive and powerful. And with semantics, we focus on alignment on common meaning rather than alignment on labels or tags. Let me explain what I mean by that. So we have relational databases, we have big data, Hadoop, we have Excel spreadsheets, we have unstructured content, and we could take the same meaning and represent it physically in different ways. So we could have an employment table where we could see Wells Fargo and David from a relational point of view, Wells Fargo and David from a Hadoop name value point of view in big data. We could make an Excel spreadsheet that says the exact same thing, and we could say the exact same thing that David is employed by Wells Fargo. These all mean the same thing from a business point of view, but they're all represented in all kinds of different physical formats. Ontologies provide a Rosetta Stone-like capability where they could understand that every single different physical representation of the same thing that's tagged differently but means the same can all be encapsulated and ingested in this ontology because it's expressive enough to link all of this information together. It'll understand that all of these things mean the same. That's actually a very, very powerful thing for reducing redundancy and creating that single version of the truth for data harmonization. Very important thing. So knowledge graphs capture all kinds of facts and relationships. Stanford is a type of university, which is a subclass of an academic institution. California is a type of a state, which is a kind of geopolitical entity. And we could say Stanford is in the state of California, and we can link all of this information. So where does this come from? Who defines knowledge graphs? It could come from experts, people. It could be done through crowdsourcing, like Wikipedia. It could be done through linked open data, which is the semantic extraction of Wikipedia, a database called DBpedia, which is a semantic database on the web. And so this can all be done also through machine intelligence, which we'll get into in a moment. So knowledge graphs can grow dynamically. So we can always add these attributes. Stanford's average freshman age is 18, again, subject, predicate, object. It may have average tuition of a certain amount, an average room and board of a certain amount, and a certain amount of average costs. And we can then, over the web, make an inference that based on Stanford's basic attributes and statistics, we might see that its tuition is 74% of the national average. This can be calculated and inferred over the web. So we can gain certain insights. So we might have a customer that makes a statement, my daughter Lisa is attending college at Stanford. So we could create a link into the knowledge graph. Lisa is attending Stanford. Now we have links to all of this other information about Stanford. We could then see that Lisa is a member of the Wilson household, and we could see again that the tuition of Stanford is 74% of the national average. Based on that, we may draw an inference that the Wilson household might be a high-value household. Therefore, they may be a lead for wealth management. So where we're going with these knowledge graphs is in the ability to draw inferences based on information that's captured in order to draw conclusions that are going to be helpful to the business. So the kind of skills that we'll be needing will be people that will understand how to work knowledge graphs and how to apply other capabilities. Knowledge graphs will also transform the web. So the web is leveraging knowledge graph, particularly through Google, Yahoo, and Bing, formed a consortium called schema.org, where they're creating these knowledge graphs that search queries on the web, such as find Wells Fargo branches in Contra Costa County open Saturdays at 9 a.m. Today you can't yet do this, but very soon you will, because it'll see in its knowledge graph that Contra Costa is a kind of county. It's not just a string, but it's a piece of meaningful information that's linked to cities like Walnut Creek or Danville, that are cities in Contra Costa out in the Bay Area where I live. Find Wells Fargo ATMs and food stores in Walnut Creek. We would then link that Walnut Creek has things that are named as food stores, so we would see relationships, subject, predicate, object. Walnut Creek has store Safeway, which is a type of food store. Find the lowest home mortgage rate, 30-year loan with 80% LTV. Banks and other financial institutions will be publishing on the web for machines to consume the various criteria for loans, for example, so that it will position us for digital agents to query the web to find the different loan criteria and ultimately produce a transaction that will recommend the best loans for you based on your credit criteria, etc. Like this next example. Find the best home mortgage refi that I might qualify for. It's going to use these knowledge graphs for loans, and it's going to link to a customer knowledge graph where all the information about me is linked. Of course, this will require authorizations and approvals by each individual to allow the linkage of information, but with the right authentication mechanisms, it would allow for the customer knowledge graph to link all of this information together so that we could infer, can you qualify for the loan? So that's one part of the equation. The other part is machine learning. So I'm going to cover different aspects of machine learning very quickly. Supervised machine learning essentially allows us to look at prior data. We call a training data set, which has all the answers that allow us to look at the past in order to develop a formula that, based on past experience, may allow us to predict the future until we gain new insights. So some of the use cases here, fraud, call center optimization, credit risk, are all examples of what we would use as machine learning, supervised machine learning to be exact. So I'm going to go over a couple of basic examples. Simple linear regression is where we could look at a graph of housing prices from the past that we could plot out, which has the ability to be a training data set. So we could look at the different variables and we have the right answers. And then we could come up with a certain formula that we call regression, where we could look at a line that says, well, if we could come up with a formula close to this line, we'll be very close to predict, based on the prior history, of what housing prices might be based on size of the square footage of the house. So we call this a regression line, and we have a formula, a very simple formula, we call a linear regression formula, that is highly predictive. There are other formulas that are much more complicated, and we move up the level of being able to be more precise because we're dealing with high numbers of variables, and sometimes a linear regression formula may not work because that slope of the line may take us below zero, and you really can't or shouldn't have in this case, a probability of borrower default to be below 0. So there are other formulas like logistic regression, which is just another statistical formula that puts it in a band between 0 and 1. So they're just different statistical techniques that we use. Support vector machines is another type of an example of a machine learning algorithm for classifying data. So in this example, we want to look at customers with high churn potential. We could basically plot these on a grid here, and basically we come up with another formula to represent a line we call a decision boundary, which separates those that might have high churn versus low churn. But in many cases, this is not as simple as a linear type of regression line. In reality, it's a lot more fuzzy. And so we might plot data that looks like this, where some of them are, it's not such a simple linear boundary in order to classify which customers will have high churn potential, which ones are low. So there are other techniques that we would learn that take this two-dimensional view and convert it to three or n-dimensional views, where we could actually much more easily look at this when we introduce another dimension. These very flat data points now exist in a space, a Euclidean space, where we can introduce what we call a hyperplane that will more easily divide these data points, so it's easier to then see how we could classify and separate the customers that have high churn versus low churn potential. Another algorithm that's very interesting and powerful, and one that's used more and more, is what's called the neural network. And these are very interesting algorithms that have been around for a number of years, but as computational power gets better and better and better, we're able to create very powerful machine-based algorithms that can basically mimic what goes on in a neuron, where in a neuron we have inputs, we have actually something called an activation function that digests the data and basically fires off when certain conditions are met in order to trigger some kind of electrical impulse that later gets translated into something in terms of thought or some kind of neural activity. Mimicking these neural networks has been a tremendous, tremendous innovation in order to use it as a machine learning algorithm for what's called nonlinear classification. So we have, for a customer, we can say that there is a risk of credit risk, or there isn't a risk of credit risk. So here again, we plot out from prior experience different customers that may have different attributes on a graph that lead us to indicate high credit risk or low credit risk or no credit risk. So a neural network looks very similar to the kind of physical neuron, where we have different inputs like financial ratios, credit risk positions, and other variables that become what's called an input layer. We assign certain weights, and what we have is, in this algorithm, a hidden layer and then an output layer. And without going into any details, there are mathematical algorithms that basically process these values coming in incrementally and iteratively with this formula, where we could eventually look at a graph like this and reproduce it with high accuracy in order to classify, based on the inputs, who is high and who is low or not at credit risk at all. It's a very, very powerful algorithm. It gets even more powerful with many of these hidden layers that process and crunch the data. And computationally, it's very extensive. But with advances in computational power, we have what's called deep learning neural networks, which are used in many very complex machine learning algorithms. So let's move on to unsupervised machine learning, another very powerful capability. The difference is that we do not have a prior answer. We don't have prior training sets in order to compare to the past history in order to create a formula to infer patterns for the future. But this is, it basically looks at the existing data, and some of these machine learning algorithms are used to separate customers for market segmentation, for social network analysis. Google and Yahoo and others use this for page ranking algorithms in Google search. So one simple example of a unsupervised learning example is a k-means clustering algorithm, where we come up with some intuition about what or how many different clusters exist. And so we have a graph of data points, and we start to identify, using this k-means clustering algorithm, it basically looks at we can define 3 points, or which we'll say are examples of 3 different clusters, and the algorithm basically starts to separate the data to align closely to each of these data points, so that we could begin to see and identify that whatever it may be, we have different groupings or clusters of data. This is a very powerful clustering algorithm that requires prior knowledge of the number of clusters. There are other very powerful clustering algorithms that do not require you to know ahead of time what the prior number of clusters are. And so those are also something we don't have time to cover. And we're just touching the tip of the tip of the tip of the iceberg of what's in machine learning. Graph analytics is another area where we basically show in a graph structure how different people, concepts, things are linked together. So we call the things or entities nodes, and the relationships between these we call edges. And sometimes we have what is called the directed acyclic graph. Here's an example where we can look at, this is an example of systemic financial risk, where through creating a graph where we can see money flows between different banking entities, we can identify a graph metric called an eigenvector. An eigenvector is like a page rank where it looks at centrality in a network. So these little numbers, 1 means that Wall Street Bank is the most influential in this network, while some of the others with the other lower numbers are the different banks that Wall Street Bank interacts with. And essentially, it looks at importance or centrality. So those different entities in the graph that have fewer trading partners are less central. The key thing here is if Wall Street Bank fails, it's going to have more of a cascading impact on the network than, let's say, if National Bank or Global Bank fails, or even Trader Inc., which has the lowest number. It has the fewest trading partners. So this is done through graph analytics, and it becomes very powerful, where we can start to look at the behaviors and the relationships of things in a graph. So another part of machine intelligence is natural language processing. So what exactly is that? And cognitive computing. So natural language processing is the ability to basically parse and understand language and understand it in context in order to get its meaning. And text analytics is really the science that converts words in documents into certain numeric equivalents in order to run various algorithms to understand similarities and patterns. And this is used in fraud detection and sentiment analysis and understanding communication. So we have semantic text recognition where we may have someone make a statement, James Jackson is planning to buy an SUV for his family. We can capture the text using natural language processing and parse it and break it up into a knowledge graph where by virtue of this statement, we could break it into these different types that James Jackson is a type of person. Again, subject, predicate, object in the knowledge graph. James Jackson intends to purchase a sports utility vehicle, intends to purchase is a synonym of planning to buy, and a sports utility vehicle is a synonym of SUV. We could break this down into triples, store it into a triple store, and then run analytics against it. Very powerful stuff. And here's just examples of breaking down sentences into subject, predicate, object forms, storing it into a database, subject, predicate, object again, where we could take this statement and parse it into its different forms. And then we could visualize it in a graph. So we could see the same thing from a verbal statement into a graph that a database can understand, and machine learning algorithms can access this data and run against it. So we could see Edward Wilson as a type of person. Requests do not block his credit card. It's a type of credit card, which is a type of account. He's traveling to England, which is a type of a country. So we get a lot of information from this visual picture of a knowledge graph that's captured from speech and communications. Now, cognitive computing takes everything I just covered, and it basically uses machine learning to incrementally improve its conclusions over time because it looks at how it can improve its learnings. So cognitive computing we can look at as an incremental iterative feedback loop into learning algorithms to improve basically the conclusions over time and to in fact select the right algorithms that are the most accurate, to use those and let others fall off, so that it's a process of incremental improvement over time. So cognitive computing is an important capability. Graph analytics, natural language processing, semantic technology, machine learning, this is all where the puck is going to be over a big data infrastructure. So what are some of the use cases for knowledge graphs and machine intelligence? So let's look at search. So in most intranet sites, we might ask, what is a consumer high-value household? But typically what we'll get back is a bunch of documents that might have these as part of the tags in the name, but without getting back the definition. What happens here, if you're not getting the definition, the real answer, but you're getting documents that just have similar tags but don't really answer the question, what we're doing is we're creating an expense in the institution. And there's a cost there. And what happens if we get the wrong information? And how do we find the correct standardized version of the business definition? And how do we find linked or related information? And how do we make sure that our operational processes will make use of the same information that's the standardized information? These are pretty big enterprise cost issues and quality issues. Well, by using knowledge graphs, we can query the knowledge graph to ask what is a consumer high-value household. It will come back, just like in Google, with an answer with hyperlinks on some of the concepts. So it'll come back with definitions, and if I want to know what is a consumer household, it'll go back to the knowledge graph, get me that definition. So this is sort of the next step. First, in human-facing knowledge capture, knowledge graphs are going to play a very, very big role in the enterprise. Another example is where we can put together knowledge graphs and machine learning is how do we allow and enable our systems to understand customer communications as well, in reality, better perhaps than people do. That's really the goal. So customers often share important information with companies through their call centers that's ultimately captured in text, where bankers write notes, call center logs, customer emails, chat logs, voice-to-text transcripts where you hear beep, beep, beep. This can be captured for quality assurance, social media. So let's say, here are a couple of examples. So Robert Otero and Julia are expecting a baby on August 15th. So they're telling someone in the organization that this is a major life event for them. Well, the organization needs to know about it, but often they don't capture that. Or Amy is experiencing financial anxiety because she can't pay the mortgage because of her husband's illness. Or Steve Callahan is unhappy with online customer service and he wants to move his accounts from Wells Fargo to B of A. Well, how do we automate the capture of this information into a knowledge graph to allow us to better provide personalized customer service, improve retention, reduce the risk of fraud, and enhance marketing efforts to market to people better? You don't want to market to someone whom you already have as a very solid customer because you don't need to expend the money, but you also don't want to market to someone who's on the edge because it may push them in a negative, unintended way. So you want to really understand your customer, and by capturing communications, things that they are intentionally telling the company. They want the company to know. The company needs to have an institutional memory. So machine learning is a way to do this. So we can capture the data through these knowledge graphs through the process I just discussed using semantic text recognition so that we could better group our customers using unsupervised machine learning and customer segmentation. Some of those machine learning analytics for predictive analytics. Prescriptive analytics is basically where it suggests how to respond to a certain condition. So by using these capabilities, if we were able to deploy this, then the system would automatically say to the Oteros or recommend to a call center person or automatically, well, perhaps we could recommend a savings account for the new baby. Maybe we'll send a congratulatory note because we remembered. We don't have to, the Oteros didn't have to repeat themselves. Or Amy Chen, who's been very upset, we could offer helpful financial advice during this predicament, a free credit score so she could track how she's doing with other companies, and recommend sensitivity during any kind of personal communication. And for Steve Callahan, we might have a banker personally reach out to him, particularly if he's high value. And we may also just generally recommend sensitivity during our communications, and also, without mentioning, understand what are the predicaments he was facing and solve those. So there's a huge opportunity here, and this is the shift. This is where data is going, and this is where the skill sets are needed in the industry in order to, you in particular, to direct your time in order to basically be at the right point in time where the puck is going to be. So what does it take to learn data science? What does it take to learn semantic graph and ontology modeling and design capabilities? That's really the big question. What can you really do, besides enrolling in master's programs or PhD programs at IIT and other institutions, which would certainly you can and should. But if you want to, if you're working full time and you want to do a lot of this on your own, there are ways that you can start to position yourselves to learn things. So online study, self-study courses, MOOCs, massive online learning courses are very, very helpful. So one that I, in fact, participated in is through Coursera, and Coursera is available online. Just Google it and bring it up. It started in 2012. It's through a professor at Stanford, two professors at Stanford, Andrew Ng, pictured here, and Daphne Kohler. Daphne was a very, very big innovator in machine learning and authored a very well-known book called Programmable Graphical Models. And Andrew Ng is very, very influential in robotics and is also the chief scientist now for Baidu, as he's also continuing at Stanford. And they offered this free online course in machine learning in February of 2012. 100,000 people enrolled. And they're now offering this course on a continuous basis. So it's a very good course. I took it, and I had to take it several times to digest it over and over again. And that's what you do with these online courses. You could take it at your own pace, and you could do it again, and you could zero in on where you need to relearn something a bunch of times. Another really, really good online course, again through Stanford Online, not through Coursera, is called Statistical Learning, and some of the two gurus also of machine learning, Trevor Hastie and Rob Tibshirani, these two guys here, here's Trevor and Rob, are authors of many books and many innovators in machine learning, and they go through this particular book in the course on statistical learning that you could then play with actual examples in R, which is a package that's free and open source that everyone can start kicking the tires on and start playing with many of the examples for machine learning. Arun suggested to me another one to add is some of the self-study courses through MIT. One that I think just everyone missed is a very good one on big data, but there are several different machine learning venues through MIT's OpenCourseWare and MIT's professional education through digital programs. So I strongly encourage folks to take a look at these courses. One that isn't a course, but I'd say a second step. So once you've started to really feel that you've gotten your arms around machine learning through your own efforts to kick the tires on this, and it's a pretty demanding stuff. It's not something that you could digest and learn in a week. This is going to take you some time. It's got to be an investment, but it is definitely going to be an investment that if you can really do this well, it'll definitely pay off, because I think that there's going to be a growing, nonstop demand for people with data science skills. And data science is not something, again, that a vendor is going to offer a product and say, here, just push this button, we're done. So companies are going to need people to understand this stuff because it's an art in many ways more than a science. While of course data science is a science, there are so many different pathways to take and so many different ways to analyze a problem, so many different solutions and combinations of solutions, that it does take a lot of experience and a lot of knowledge, and that's where the art of it comes. One way to really develop the skill further is through companies that are emerging like Startup.ML, which you could Google. They're a relatively new startup company themselves, and what they are planning to do is they're creating this notion of a data fellowship. And what they do is they take, first they test people on their skills in machine learning, but it's for new people, for novices, for newbies that are learning on their own. Is exactly for you. And what they'll do is they'll place you in a company as a fellowship where you can learn on the site of the company, and you're mentored by the principals of Startup.ML that are experts in machine learning. And so it's sort of a way to help companies gain new employees that have skills in machine learning, because you just can't go down to the local Starbucks and find someone. They're already grabbed up. This is a high demand area and will be a growing demand area. So Startup.ML is very cool, and you should definitely ping them, perhaps even before you get started, and ask them for some insight also on what you could do to get started. They're very nice people. Other ways to learn is just, without doing an online learning course, you can just get a book. So here's one really good book, Machine Learning with R. R isn't the only language for machine learning. There are many of them, Python and MATLAB and Octave and a whole bunch of them. But R is really, I think, the most popular, and it's one that is being recognized by the enterprise as a skill that is needed. So you can just buy a book like this one, which I thought was great, really easy to start, very well written, and you can work through by downloading R and RStudio, which will allow you to go at your own pace and actually program the various different types of algorithms. The other thing is there are meetups, meetup.com, where people in your local area are interested in R. So here's the one, the R meetup in San Francisco, and there are, I'm sure, R meetups in many of the major cities where you might be. So this is a very good way to learn as well. Semantic technology, very similar, meetups in semantic technology, but you can learn on your own. The best book out there, Semantic Web for the Working Ontologist by Dean Alumni, is a good book to start reading. To start working with semantics, you could download Protege from Stanford for free. It's a ontology editor that will allow you to actually build your own ontologies bit by bit and gain expertise. They also have a tutorial called the Pizza Tutorial, and they take you step by step on how to build a pizza ontology. There's also one done by the W3C on a wine ontology. So I'd like, it's always good. Pizza and wine go together. There is none on beer yet. So you might create your own ontology on beer and link that to the pizza ontology. But this is a good way to get started with semantic technology, the basis for knowledge graphs. And then lastly, there are many conferences, one that I like, Predictive Analytics World, and they travel around the country. There's one in San Francisco and Washington, probably one in Chicago, and that's a really good way to get started. Is conferences both in predictive analytics. Smart Data Conference is on cognitive computing. It's on semantic web technology. It's on machine learning. It's on NoSQL. It's on big data. It puts it all together. And this upcoming one in about a month in San Jose, and they have smart data conferences also across the country. So that's about it. We've left a few minutes for Q&A, and let me turn it back to you, Arun. And if anyone has questions, I'll be happy to answer as best as I can.
David, Thank you very much. I hope everyone can hear me. If you have questions, let's use the chat function. Should be on your menu on the right-hand side of your screen right now, or you may need to expand it so that it drops down. Well, I'm not seeing any questions. I certainly think that we've covered the gambit today, and I thank you for showing us some ways in which people can further their learning in this topic. Well, we do have, what is the future of machine learning, David? I see that popped up right now in the chat.
Yeah, machine learning is, truly going to be the wave of the future. It's already the wave of today. It's really something that is a prudent investment in terms of gaining skills in that area, because we're going to be relying on computational capabilities to connect the dots more and more and more and more. It's going to be transformational for our society. Just look at the Google self-driving car based on machine learning. It's going to transform our world in ways that we do not even know about. I'm not sure, there are all the ethical questions raised, from Stephen Hawking to Bill Gates and others that, say we better tread with great caution into this whole machine learning space. And, I think that is prudent to think about all the unintended consequences and the ethical questions about this. What does it mean? Will it create massive unemployment? Things like that. My thinking is that, just from looking at all the fears of the past in the industrial age and the age of computers, there was always the fear that people were going to be displaced by industrialization and automation and computing, and it has never happened. It's only created and stimulated new industries and new opportunities. So I don't fear it. I think we have to be careful with our, with our eyes wide open about it. I don't see the singularity or Skynet as emerging in a dangerous way. Those are all the science fiction fears. But I think it's something we have to be prudent about, and hopefully it will be a force of good. It is going to happen. So it's not even a matter of question. The puck is moving in that direction. There's no question about it. So I think we have to do our best to position ourselves to exploit it for our own benefit. And the folks in the information technology field are very, very well positioned to take advantage of it.
David, we've got a question.
So what is your best suggestion? Go ahead.
David, we've got a question. When it comes to big data mining for machine learning, there can be privacy concerns for all the personal data is being harvested. Can you please comment if there are privacy concerns?
There are privacy concerns, and companies are under many, many guidelines legally to respect and honor privacy of customer data. So that is something we take very, very, very seriously. And so it's always a legitimate concern of what can we link together. And so we always and must consult with our legal staff on, what information do we want to connect the dots on, what information are we prohibited from, so that we ensure that customers' privacy is respected. And I think this is going to be an area of discussion and debate going forward, in all industries that leverage customer information. And I think we're going to see the emergence of what's called a customer data ecosystem and customer data lockers, where there's going to be development of capabilities where customers are going to be able to more automatically manage the privacy of their own information. So it's not as much where, okay, now that once Facebook has it, it's always going to be out of my control. I think there's going to be shifts in that, and there's been lots of discussion, with the lawmakers. So I think we're going to see changes in this area evolving. It's not quite yet settled. It's an interesting area and an interesting question.
David, I think you saw the other question. What is your best suggestion for someone who is just about to start with the ML field or wants to join this area?
So, I think I would do a little of some of things that I covered. I would try an online learning course. Probably the machine learning through Andrew Ng was really, really good. And I would get a book on machine learning in R and download it and do both. I think that, depending on your time, that would be prudent. But that's where I would start.
Great. I don't see other questions. There was a question that was posed, where will we be hosting this webinar? We will send you a link, as well as others who registered who weren't able to attend today, for the webinar once we get it posted, and then that will direct you to the other series that we have recorded, and you can check back to that. It will be off the alumni.iit.edu website, and it'll be on the careers tab under professional development, but you'll need to give us a day or so to get that up. So with that, would like to thank everyone for joining us today, and certainly thank David for your thoughtful insights on this topic, and would conclude our program.
Thank you. My pleasure.